Hello, this is Cyprien again, and in this video we'll talk about Salome CFD. So it's the first video I'm doing about fluid dynamics, so I hope it will be very interesting. So here I just opened Salome CFD, which is different than Salome Mecha because it integrates Code Saturn. So you have it CFD Study, it's the module of Code Saturn. And this is the solver that I will use for CFD. So you can see the icon Salome CFD. So how do you actually install Salome CFD? Well, to install Salome CFD, you have to go on the website of codesaturn.org, and then you have a link here, Salome CFD. You click here, and you go on this page, and then it tells you that you have to download it from the Salome website. So if you click on this link, you will find this page where you have different versions of Salome. So Salome Mecha, Salome Hydro, Salome CFD. So Salome CFD is the version of Salome which integrates Code Saturn inside. And you have two versions right now. You have the version with Code Saturn 5.0 and Salome 8.3, and you have the version with Code Saturn 5.2 and Salome 8.5. So it's important to mention that there is a big difference between those two versions. First of all, Salome CFD works the best on a Debian system. So if you have a Debian 8 system, this is the best to run the Salome CFD. If you are on Ubuntu, this first version won't work, so don't install this one. The second one works, so that's the one I installed right now, but there are still a few problems in the interface, so you'll probably see during the video a few glitches, and the multiprocessing will also not work correctly. So but I hope a version for Ubuntu will be released soon. Now if you're on Windows, I'm sorry to say that you won't have a Salome CFD version for Windows, but you can still use Code Saturn on Windows. There is a version of Code Saturn for Windows as well, so you can search on internet how to find it and install it. Okay, so now let's start the tutorial. So I will start with a very simple flow analysis of a simple channel, and the first thing I'll do is to create this model. So let's go into the geometry module, in which I will build the model that I will use for the CFD study afterwards. So I will do, for the sake of simplicity, a 2D analysis, but you should know that you need still to have a 3D model, but it will have only one layer of mesh on the Z direction. So that's how Code Saturn process the model. So you still need to have a 3D meshed model, but it has to have one layer of mesh on the thickness. So I need basically for this just to build a box. So my model will be very simple. In X direction it will have a length of 1, on Y direction 0.1, and in Z direction 0.01. Apply. Now let's scale up. So now I have like that a block, and now we have to think, what do I need for to set up the mesh and make this model ready for simulation? Well, I need to create the groups, so I'll do that. But first, you need to define the size of the mesh, right? So as it is a block, there is a function which is very useful called block propagate. So you'll see what it does. I select the object and it creates 3 sets of edges which are in each of the directions, and I will use those sets in order to define the submesh in order to assign a size to this. So let's change the name just for the sake of simplicity again. So in Y direction, okay, I'll call it Y there, and the edges, well, those one are X there, right? Okay. Okay, now that I have that, let's create the groups that I will use to assign the boundary condition of my CFD analysis. So let's go in new entity group, create the group, select my model and select the shape type face, and let's position this in this way. So my inlet will be on this side, so I'm just, oh, I didn't select the right shape. I have to select the box here. Okay, I don't know why it's not selecting. So let's try again. New entity group. Okay, now I'm selecting the box. Right. Okay, select the inlet, add, let's call it inlet. Very original, I know. Let's select the outlet, and let's call it outlet. Apply. Now the top face and the bottom face will be wall conditions, so I'll just call it walls. And don't forget that I have to demodel, so I need to assign symmetric conditions on the two faces, which are actually symmetric. So I'll just call that symmetry. Okay, so now I have 4 types of groups, and I have a box, which is basically my my model that I will use. So my geometry model is complete. Now I will go to create the mesh. So let's jump to the mesh module and activate our geometry. So the first thing to do is just to add a new mesh set. And I'll do it simple. If you go in this tab here, you have automatic hexahedralization. So I will use that. I will not use the basic type of hypothesis because I will define my own size. Okay. And now I have to give it sub-mesh. So in each direction. So in Z direction, wire discretization with only one segment, so number of segment 1. Apply. Now in Y direction, I will define 20. Okay, how many segments? Let me think. 24. I will do a small model, so it will go faster for solving. And let's just call it like that. Apply. And in X direction, I will do 8 segments. Apply and close. Now I have one mesh and 3 sub-mesh defined on the edges, like that, so I can compute my mesh. Okay, and it looks like I didn't assign correctly my my sub-meshes. So let's take a look what happened. So Z, okay, let's hide the box. Oh, okay, so Z direction, it's actually showing me along, okay, it should be correct. Y direction, yeah, and X direction, I think it's correct. Maybe I got it wrong here. Z direction 1 segment, Y direction, okay, in y direction I want only 8 segments. So let's just edit the hypothesis. Let's just change that 8 and 24. Okay, and now I can just recompute again. Okay, now I'm getting the right mesh that I wanted to get. So this is my my mesh. So I'll apply an inlet here, I'll apply some wall condition, and I will take a look at the outlet. But before that, I need to create the groups of the mesh, because I created groups for geometry but not for the mesh, so I have to use the function called create groups from geometry. Select my mesh, select my groups here, apply. Okay, so, and I think if I'm not wrong, it's okay, so it's good for the mesh step. Okay, let's go to the next step, which is the definition of the CFD study. So that's where you see that there will probably be a few bugs of the interface, but I hope everything will be fine normally. So once you open the module CFD study, what you have to do several things. First, go in view window, toolbar, sorry, activate the CFD study toolbar. So this is the CFD, the toolbar corresponding to the Code Saturn interface, and we will create a new CFD study case. So in this window, create study. Now find a place on your computer where you can save that, and let's just give it a name, case 1. So you can do several cases after, you can change the mesh, copy cases quite easily. So this is why I call that case 1. And when you click on OK, you see that it creates something here in the object browser, which is the CFD study. So you have some folders that were automatically created, and those folders include the different things from Code Saturn. So Code Saturn will take the information in all those files in order to compute your analysis. So the first thing we need to do is to put the mesh into this mesh folder. Right now I have my mesh into my preprocessor, but I need to give it to Code Saturn. There is no direct interaction like that, like in Salome. So I have to go back to the mesh module, click here and export my mesh, and let's find the folder where I put it. Okay, and here you have a mesh file, so I just save that here. Okay, now we are ready to open my so we activate the CFD module again, and if you open the data tab, you'll see that you have something called Saturn GUI. So let's click on launch the GUI, and once you open the GUI, you have to save it. So click on the small drive here, and when you click on save, you see in the object browser that you have a setup.xml file which appeared. So this everything you define in the GUI here will actually be saved under XML format into this file. So XML, if you're not familiar with XML, it's a bit like HTML format, but it allows to define your own tags. So it's kind of format used by different interface to dialogue together with some data. So you see that if you don't have the GUI of the Salome CFD, but you have this XML file and your mesh file, well, you can use the command line interface to compute and get the results, which is sometimes faster than go over everything again graphically. Okay, so let's start. So now I have my GUI. So this is the GUI of Code Saturn on the right, and this is the first tab. So you have here, if I click on Mesh Selection, you see that it's automatically opened the folder Mesh, and now I have to click and add my mesh inside. And that's here that you see there is a small bug appearing. The window is kind of, I don't know why, automatically putting here because I think it's not totally compatible with Ubuntu. So what I will do is just you take off this window and put it here like that, floating like that, and then I won't have any problem after that. And I can, put my model like this, and now everything is fine. Okay, so now what you have to do to define your CFD analysis is go over all those small folders here on the left. So mesh selection, we already did it, so I added my mesh file. Now we have to go to thermophysical models, sorry. And here in calculation features, that's where you define, the first one is the most important in this case. So I will calculate steady flow, not unsteady. So steady flow, nothing else to define here. Okay, turbulence model. For this case, I won't use any turbulence models, so this will be a laminar flow. So I'm just defining it like that. Physical properties, okay. Reference values, well, I don't need to change that. Fluid properties, okay, so here I need to define the properties of the fluid. Reference value, so I'll put density of 1000 and viscosity of 100, and that's it. Gravity will be null in this case. Remember that if you want to consider the effect of gravity, well, you have to define it here, minus 9.81 or minus 10, depends on, well, you have to define it here. It's not automatically considered. Now go in volume conditions, okay, initialization. So initialization is basically the initial value of the velocity. So I'll just put 0. So which means actually it's not so important, but it may have some kind of impact on the convergence in some cases. The way you initialize the velocity. I'll define a velocity which will be equal to 0.6667. So actually I could also define it like that here, but 0 is okay as well. It will converge, no problem. Now boundary conditions. So boundary conditions, you have to define a boundary condition here. So you can add them directly, or you can add them from Salome. So for that you have to go in the object browser, you find your groups that you defined previously and click on add from Salome, and you will see those appear here. And if this doesn't work, sometimes it doesn't work, what you do is just add, and in this column you just remove everything and you write the name exactly of your group, and then it should work. So the name here in the selection criteria should be the same than the name of your group. Now let's change the name, the labels of those boundary conditions. Okay, and here the nature, so it's not obvious, but what you have is double click here. You have to double click here and you'll see the type of boundary condition appearing. So you have to set up inlet to inlet, outlet to outlet, walls to wall, and symmetry to symmetry. Okay, now I set the boundary conditions regions. Now you go in the next tab, boundary condition, and that's here that actually give it, you give a velocity. So let's expand a bit. The norm here, okay, I'll just give it a value of, so I want 0.66667. So I could also give it a formula. Maybe this will be a bit better. Norm user load. Then you click on the button and you can define it like 2, and don't forget the sign at the end. And it's the same actually, but it's a bit more accurate. And that's the only thing I need to define for the boundary condition. Everything else will be automatically defined. So very simple boundary conditions here. So just explain what I expect to get. At the entry, I'm putting a constant velocity here, but when the fluid flows along the channel, at the boundary, at the walls, the velocity is should be null. So the profile, in a parabolic profile, velocity will develop along the pipe. So at the end, I want to have a parabolic profile